Good afternoon, everybody, and thank you for the introduction. Um, my name is David Griffiths, as said, and very pleased to give the presentation today to give an introduction to digital trains. So before I start, I'll also introduce some of the team members who I think will also be on the call. So as well as myself, we have Dr. Terry Williams, who's a research director behind Digital Trains. We have Simon Reed, principal analyst, Daniel Taylor, principal software development engineer. And we also have Javier Rincon, business development manager, Timo Schultz, global sales manager, and then Ryan Yend, regional sales manager. So we'll start with an introduction to digital trains, just a bit about what the software is also. So yeah, so first question, so what is digital trains? Well, it's a advanced cloud-based platform in which complete rail projects can be digitally created within a single environment. This allows users to analyze and compare total train performance across any route in the world and helps optimize decision making at every stage of a rail project. Digital Trains is built on proven rail technology. So within Digital Trains, we are incorporating the world-renowned Vampire Pro simulation software, alongside with Olio's longitudinal dynamics code within one single platform. This allows us to create a comprehensive and user-friendly rail simulation package. And these foundations enable digital trains to support real-life correlation and showcase project performance with clarity and great confidence. So what is our vision behind digital trains, or what was the vision when it was first created? So we see that rail projects continue to grow in complexity, and traditional methods to deliver these projects can lead to fragmented workflows, which can cause delays and additional costs. But by taking a virtual approach of simulating and optimizing the trains and the infrastructure prior to any physical work beginning, we can reduce these risks, we can accelerate the project delivery and ensure safety, performance and regulatory compliance is always achieved. This in total leads to a more efficient, innovative and sustainable way of managing railway projects. And how does Digital Trains make this possible? Well, by bringing together all parties of a project, from initial planners through to the final decision makers, into one single collaborative platform, Digital Trains will allow everyone to work from the same up-to-date information throughout the complete cycle of the project. Therefore, the vision behind Digital Trains is to make railway digital twin technology widely accessible to the industry. And this is done by providing extensive libraries and collaborative tools online in a cost-effective manner. It allows us to make advanced digital twin capabilities available to the broader range of stakeholders and not only limited to the technical specialists. And by taking a holistic approach to modeling the complete railway as a single system, Digital Trains enables every stage of the project to be undertaken collaboratively within one integrated environment. So here we see a typical life cycle of a new rail project. Won't go into it in detail, but I think what's clear we can all say is it's complex and many parties need to collaborate. And this is where Digital Trains has been designed to add value at every level of the rail supply chain. So from operators to regulators, right through to the component suppliers and maintenance contractors. So for example, if we start at the top, project planners, these could use Digital Trains to evaluate options to meet project goals, such as scoping different route alternatives, estimating energy consumption from the train and travel times up and down a route. Safety authorities, these could be used to support standard compliance, safety case assessment and technical validation. Rail operators, they could use the tool to assess real-world train performance, maintenance strategies and infrastructure compatibility. We look at design consultants. These can benefit from having a powerful web-based tool that enhances collaboration and accuracy in both planning and analysis. Track work contractors, can use the software for clearance studies and route planning. as we'll talk about shortly in the presentation. Then we come to rolling stock manufacturers, where with the impact simulations, for example, can be done full train simulations, crash worthiness assessments during the design and approval stages, but also for gauging as well along the route. And then linked with that, we have the subsystem manufacturers who would benefit from the platform's ability to simulate the inter-vehicle dynamics and and validate the energy absorption performance. And then finally, the maintenance contractors who could use digital trains to simulate repair scenarios and optimize lifecycle support, for example. So how can this collaboration be achieved through the many features within digital trains? So route planning, using the inbuilt mapping tools within digital trains, any route in the world can be digitally created in great detail with curvatures, gradients, etc., all included. We'll shortly touch on this in more detail and have some slides and examples of how this is created. Infrastructure and track, so digital trains includes tools and libraries to create track components and infrastructure features such as tunnels and bridges to aid the train running and gauging analysis. Actual stations, so we can devise stations and platform lengths required for a given rolling stock design. For the rolling stock itself, we have detailed libraries within digital trains that can be used to build accurate digital twins of any rolling stock, including suspension and crash energy management systems, which can be defined and optimized to maximize the performance. We also have buffer stops or arresters, as they're also known. These are the end-of-line protection to safely prevent the rolling stock from overrunning the available track. So these can be fully designed and optimized within digital trains. Train operation analysis. So using the train running module, we can optimize train performance throughout a designated route. And from this, a multitude of data can be extracted from the train running simulations, such as energy usage from the train, wheel to rail wear, ride comfort, power consumption, derailment risks, etc. And then gauging analysis, so using the infrastructure tools mentioned above, the gauging modules allow the user to analyze clearances and identify potential clash conditions along any given rail route. And finally, the train impact analysis, so we can analyze rolling stock safety performance during coupling and crash situations, working in line with international standards such as EN 15227, which is the key standard within Europe for crashworthiness. So some of the features and how we build a project, etc. So at the start of any project, first thing needed, a train route is required. And within digital trains, we have inbuilt tools to allow users to easily create accurate long routes anywhere in the world. These are then used for evaluating options that influence train operations, project costs, and timescales. So route planning can start from existing railway maps, from digital maps to GPS, survey, or other measured data, all of which can be uploaded into digital trains. Digital trains also include options for elevated sections, tunnels, embankments, curves, cant, and platform lengths. And markers can be placed at any position along the route to replicate braking and traction events or speed limits of a route. And again, the benefits this can give to any user, so it can allow operators to maintain up-to-date models of their existing tracks. It can be used to utilize measured track irregularity data to easily simulate the effects on train operations, to compare existing and new rolling stock performance. And also it can allow operators to select the most appropriate route and specifications for new rolling stock. So in addition to route, any rail project also needs a train. And DigitalTrains Train Builder module, this allows users to easily assemble a complete train, utilizing the many standard trains built into the public library, which can then be configured to create an actual digital twin. So each vehicle, which again is configured separately, we'll show us on the next slide. Each vehicle within the train rake is created separately with dimensional inputs to match the real cars. But alternatively, 3D CAD models of an actual vehicle can be directly loaded into digital trains. And any car body deformation or crush zone characteristics can also be inputted into CSV format, inputted into digital trains in CSV format, and then used within the impact simulation. So again, this could be test data, etc., can all be uploaded and added to the digital twin. As mentioned, so digital trains is built on libraries. So we have public, corporate, and personal libraries. And includes libraries for bogies, for crash and crash absorbers and couplers, all of which can be configured into your train. And again, benefits for users here. So this allows vehicle manufacturers to select the most appropriate vehicle geometry and crash energy management components for new rolling stock designs. So within the vehicle builder, digital trains contain standard vehicles, as well as tools to build more complex models. So these can be of the manufacturer's standard geometry for the vehicle, or specific car designs can be designed within. So we'll look into the bogie and coupler builders next. But as you can see on the video, these can be added to the vehicle to allow detailed and accurate head-to-head performance comparisons, which again can be run across any specific route and then simulated and compared as what-if scenarios. So the vehicle builder is designed to easily create complex rail vehicles that can then be configured into complete trains. So this allows operators to maintain up-to-date models of their existing rolling stock. It can allow bogie manufacturers to showcase performance improvement, and can allow vehicle manufacturers to select the most appropriate CEM system for their new rolling stock. So we talk about bogies. So the bogie builder, this again contains libraries of industry standard bogies, as well as giving users the option to produce specific bogie designs. These can include all the necessary suspension system components needed to create a complete digital twin. And as mentioned before, the created bogies can then be added to vehicles and into trains to allow detailed and accurate simulations across any given route. So this allows bogie manufacturers to showcase performance improvements with data-driven simulation evidence, and allows vehicle manufacturers to then select the most appropriate bogie design for their rolling stock. And finally, the coupler and anti-climber builder. So this is where the train's crash energy management system can be configured and optimized. So how the crash energy management system can be configured and optimized to ensure the train impact and operational requirements are achieved within a project. Within the public libraries, we have standard coupling elements such as the mounting pivot assemblies, the various coupler heads which are used, and the common absorption technology used across the industry. This then gives the user all the building blocks needed to build any coupler type. Once the couplers and crash elements are created, these can be added to the train for the detailed impact and train rescue scenarios, which we'll cover when we look at those sections. Digital Trains also enables optimization of the couplers and the anti-climber performance to ensure the mandatory safety standards, such as EN 15227, are being achieved. And then this gives benefits again to the vehicle manufacturers to ensure the most appropriate crash energy management system components are selected to meet these standards and can be designed into their new rolling stock. So what we're showing here, so here's a typical process followed by train manufacturers when designing new rolling stock vehicles. If we start at the bottom, phase 1 and 2, these are the initial concept design stages. But then really it's phase 3 and 4 where digital trains can be a powerful addition to the process. At this stage, a digital twin of the rolling stock can be created within digital trains, and impact simulations can be run to define the crash energy management and the bogie systems needed to meet the end user's needs. This can then allow the performance and dimensional specifications of coupling system to be frozen with great confidence, and allows the detailed structural analysis, which is phase 5 onwards, to be performed with reduced risk of further needs to modify the carbon geometry, which would then cause the need for the structural analysis to be redone time and time again. Following the completion of the FE analysis, the RFQs for these components can then be released to potential suppliers with the coupler and anti-climber specifications and, most importantly, the vehicle geometry being fully locked. So throughout there are 3 available modules within DigitalTrains. The route and train builder features shown in the previous slides, these are available in all 3 modules, but now we'll look at each of the modules in more detail. So we have DigitalTrains gauging. This is for clearance analysis, ensuring the trains are compatible with existing or proposed infrastructure. DigitalTrains Train Running, so this is for simulating longitudinal dynamics and the interaction between the wheels and rails under real operating conditions. And the third one is DigitalTrains Impact for the impact simulation and crash energy management sims. So looking at gauging analysis, DigitalTrains stands out with comprehensive tools for static, kinematic and dynamic simulations. What this means for the user is accurate clearance assessments supported by intuitive tools that let them easily create and compare vehicle and structural profiles for new or existing projects. The built-in visualization tools make potential clearance issues easy to spot and easy to resolve early in the design process. For train running simulations, DigitalTrains is not only simple to use with a smooth interface, but it's also uniquely integrated with the proven Vampire software and extends those capabilities from just simulating individual vehicles to having the ability to simulate full train sets, complete rakes. This means we can accurately model the inter-vehicle dynamics, including how the energy absorbers behave across the entire train. And one of the standout benefits here is speed. So we're talking simulation results in just a matter of minutes, not hours. And then for impact simulations, DigitalTrains combines over 35 years of experience with Olio International's longitudinal crash code and Vampire Pro, creating a powerful all-in-one solution. With the experience behind DigitalTrains, we have many examples of close correlation between simulation results and actual dynamic testing, a necessary requirement of international standards such as EN 15227. DigitalTrains also allows users to design the performance of complex velocity-sensitive devices such as gas hydraulics, which you use in the couplers. This is done at the touch of a button with the optimization tool, which is inbuilt into the software. So all modules within DigitalTrains are hosted on a collaborative cloud-based platform. And this is a major advantage when speaking to engineers using the software, working on crash scenarios or operational simulations, as the ability to share their models with team members, with customers, etc. The models and the simulations. This makes the whole process extremely quick and easy. So we'll take a bit more of a deeper dive into each module now, and we'll start with the gauging. So DigitalTrains gauging, how DigitalTrains can be used to evaluate and plan route options, analyze clearances, and identify potential clashes or issues along a new railway infrastructure. So when designing a railway route, there are many requirements which must be incorporated to ensure a smooth ride at the intended line speed. These must also be combined with operational and geographical constraints. The alignments, for example, must pass through all required stations, enter and exit the correct directions, and avoid existing built-up areas and natural obstacles like steep terrain, large rakes, etc. Therefore, all railway tracks consist of many straight and curved sections, and in order for a train to transition smoothly between a straight section and a curved section, or between two curves of different radii, transition curves, shown here in the orange line, are used. These curves gradually change the curvature of the track as the train enters or leaves a curve. To further improve the smoothness of this transition curves are usually incorporating super elevation, where the outer rail is gradually raised relative to the inner rail. This is done to reduce lateral forces on both train and the track, to improve passenger comfort, and allows trains to navigate curves safely at higher speed. And the rate at which the super elevation is applied depends on the design speed of the trains expected to use the track. This in turn dictates the length of the transition curve, with higher speeds requiring longer transitions. And all of this can be accurately modelled within DigitalTrains. So by using DigitalTrains' detailed routes can be created, and which fully adhere to these complex requirements when designing a new track, a new route. Furthermore, this can be achieved in one of three ways. So firstly, we can manually use the tools provided within the software to calculate the required transition curves and cants. This method can also be used to enter survey data. Next method, we can upload GPS data or follow the route on an online map. And thirdly, we can define the rules the route must obey for each section of the track, and we can enforce them as the location the track is entered by interacting with an online map. And this is a method which is being demonstrated in the video on the right-hand side. So whichever mapping option is chosen by the user, to create a route profile, he or she can do the following. So they can set the initial location and view it on a map. They can define track gauge and track profile. They can superimpose an irregularity file. They can produce both horizontal and vertical profiles. They can convert or download a Vampire formatted file. They can add structural gauges, or they can add markers where braking or traction events occur. And then if we look at gauging itself, so what is gauging? Well, gauging refers to the process of ensuring that trains can safely pass through the physical infrastructure of the railway network and will pass collision-free through infrastructure such as tunnels, bridges and platforms. This approach to gauging varies greatly from region to region around the world. So within DigitalTrains, we've taken the approach of providing 3 types of gauging analysis to cover these broad range of options. So we have static. This considers the vehicle and the infrastructure dimensions at rest, not accounting for movement. We also have kinematic gauging, which introduces the effects of suspension to analyze the kinematic envelope of a vehicle within the limit of its vertical and lateral suspension movement. And then thirdly, we have dynamic, which is a full 3D assessment of a train's movement along a route, with swept path being generated and detailed clearance assessments available at any point along the track. So when creating the gauges, so within DigitalTrains, users can easily create both vehicle gauges and structural gauges. For structural, which is shown on the left-hand side, the user can create their outline of various structures, and what we show here is an interior profile of a tunnel. And then vehicles on the right-hand side. So when creating vehicles, the user can define the vehicles in 3 parts. We have the upper part, which represents the vehicle body, the lower part, which represents the area where the bogies are, and then we have the footstep in the middle. Structures, or those structures created, they can also be added along a route. And when defining structural locations, the user can control if the footstep should be considered or not. So for example, on a passenger train, the footstep might be considered on a platform itself, but then when the train is in travel, it's then retracted in the vehicle and not needed for the rest of the travel on the track. So for static analysis, and then in the static analysis, we consider how the vehicle outline interacts with a simple structure. Here, the user can modify the cant and vertical offset, thereby testing the vehicle moving close to the structure. So in the given example here, on the screen, we have a clearance limit, or we've set a clearance limit of 250 millimeters. And DigitalTrains has highlighted an infringement along the roof of the tunnel of 240 millimeters, as you can see in the red text at the top. So again, visual feedback where those limits have been exceeded. In addition, to the system automatically highlighting any clearance infringement. The user can also manually measure between any 2 points. So this is useful for assessing platform clearance to the footstep as shown in the example here. For the kinematic analysis, here we consider the limits of the vehicle's movement on a suspension, and we drive the vehicle through those limitations step by step in every direction. And doing this allows us to build an envelope of all the possible vehicle's movement on a suspension, which is shown by the purple lines. This then gives an envelope. This then allows us to build an envelope of all possible vehicle movement on a suspension, and that can then be used as the new vehicle gauge to run through the structural gauges on the route. And then finally, the dynamic analysis. So this builds upon the train running module to allow for a full clearance analysis along a route. So as shown in the image, the orange is used on a bar graph representing the travel along the route, and also therefore to indicate positions where infringements may occur. So this complete whole route analysis can then be combined into a 3D swept path. This calculates the area that different parts of the vehicle will sweep through when it travels along a route. It considers the vehicle gauge and the vehicle's dynamic behavior by combining all the individual clearance tests along the track in one continuous swept area, which you can see there, the green sweep. This 3D view allows the users to see the route, structures, and the vehicle movement through that space. And again, through this animation, the vehicle can hone in on any position on the train, any position on the route, and do their analysis. So we'll move on now to the train running module. So example here, how digital trains can be used to simulate train operation and inter-vehicle forces across any given route. So as mentioned before, Digital Trains features an enhanced version of Vampire Pro. With the addition of couplings and expanded memory, Digital Trains allows for the simulation of entire virtual trains traveling along comprehensive virtual routes. Additionally, it can accurately simulate the longitudinal forces resulting from braking and traction on designated track geometries. And why perform train run analysis? Well, we do this to determine longitudinal forces and accelerations experienced by the train on a specific route, to compare operational performance between different trains, i.e. comparing the efficiency of one bogie design versus another, to conduct derailment risk assessments, ensuring safety margins are met, to evaluate to evaluate the wear on wheels and rails, which can be used to support maintenance planning. We can assess the energy consumption and therefore calculate the train's carbon footprint. And we can also use it to verify that ride quality meets specified comfort standards. And here we're showing an example project where Digital Trains was worked on with a major European rail operator, and the software was used to massively reduce their annual maintenance and repair costs. So based on data provided by the customer, this 100-kilometer route was created within Digital Trains. This included all vertical, horizontal profiles plus cant, and was verified through the mapping features within Digital Trains. Test data supplied by the customer allowed us to verify the digital twin model and buffer performance, and markers were then used to replicate where the train accelerated and braked to meet the line speed limits. Once this was set up, alternative energy absorption types were then analysed and compared to the existing buffers in a bid to reduce the inter-vehicle forces and reduce the vehicle damage which was occurring during the train operation, and which was leading to very high kind of repair costs year on year for this operator. So to validate the model, the results of the digital train simulations were compared with the measured test results. The top data shown, this is a stroke recorded during the tests of the two side buffers, so left and right. So the top one is the left, bottom one is second one is the right. These measurements were taken at one particular interface on the train between the second and third coaches, and then when compared to the same interface to the results from DigitalTrains, we showed good correlation against the simulated section of the route. And this can be seen by the trend in stroke along the route, and the x-axis is the distance travel. But again, you can see the trend between the DigitalTrains output and the actual measured test data. Within DigitalTrains Train Running module, we also have a wheel-to-rail contact patch calculator. So standard wheel and rail profiles are built into DigitalTrain libraries for all users to access, but also with tools available to create different profiles. So for example, a worn wheel or a worn rail can be created for comparative simulations and studies. The contact patch generator allows the contact patch to be calculated, and the size and position can be reviewed at any lateral position. The point plot, this shows specific areas of the contact between the wheel and the rail. The wheel-to-rail forces dictate the level of wear damage that can occur in real life, making this an extremely powerful feature within DigitalTrains. And if we run a train running simulation, we can view the results as a 3D animation, as shown on the left, or we can view output from the virtual transducers. So within DigitalTrains, it allows the users to monitor all aspects of the train via virtual transducers or measures, which can be added to any component within the built digital twin. So firstly, the first graph here, we're showing lateral force acting between the wheel and the rail. This next graph, this shows a ratio of vertical and lateral loads. This is a parameter frequently used to measure derailment risk, and ideally we want to keep this value below 1. And finally, this graph shows T gamma, which is the energy dissipated per unit length of track, and this is a measure commonly used to assess wear. So when using the software to measure or to simulate derailment risks, the 3D visualization can help determine the point along a route where wheel lift or, in severe cases, derailment may occur. So in this example here, which is based on a full-size test which actually happened, a derailment occurred as the freight train traveled through an S-bend. And then in 3D, in DigitalTrains 3D viewer, we can clearly show the point in which the wheel lift occurs. So it's the last wheel on the green part. It just begins to lift as it goes across. If I go to the next slide, we just have a still snapshot just to show the wheel lift occurring. So again, visually very powerful just to show when it happened. And again, from the transducers and the output results, we can then measure the exact extent of what has happened. And then finally, we'll take a look into the impact module and how DigitalTrains can be used to specify the correct crash energy management system and ensure compliance with mandatory crashworthiness requirements, such as the aforementioned EN 15227. So first of all, what do we mean by impact simulations and why do we perform an impact analysis? So crash energy management systems, they control where the impact energy is distributed within the train when a collision occurs and ensures the vehicles do not override or derail. Modern trains are designed to perform to crashworthiness standards, and in Europe, this is the EN 15227. So DigitalTrains allows analysis of the performance of the train beyond the requirements of the current standards. So for example, we can also simulate impacts on a curve or impacts involving trains with uneven loading. We also have buffer stop analysis to ensure the end of rail arresters are sufficient to stop a train in the event of an overrun. Very important for protecting station platforms and commuters. And then the optimization of coupler interfaces. So the performance of inter-vehicle energy absorbers can be optimized in the simulations to minimize impact forces and to improve the train durability, and therefore to reduce decelerations experienced by the passengers. And here we just have an example here. So this was an example from the French rail operator SNCF, who've used digital trains to create twins of all their rolling stock. And where applicable, they've compared to actual impact tests, which they previously performed. So the example we're showing is of their Regionalist train, where coupling tests were performed in 2014. And through digital trains, we're showing good correlation between the full-size vehicle impact tests and the digital twin simulations. So top and bottom graph are of different impact speeds, but the orange curve is the output from digital trains overlaid against the actual test curve, which is the yellow. So again, we're showing very good correlation. And traditionally, crash energy management and coupling stroke shunting acceptance criteria have all been analysed on straight and level tracks. But by integrating Vampire Pro's wheel-to-rail simulations within digital trains, this enables more comprehensive three-dimensional analysis. And this therefore allows us to evaluate how the crash energy management of a train is influenced by impacts on a curve and the associated derailment risks. So if we look at the animation from overhead, the interaction of the anti-climbers and the subsequent effect of the dynamic side loading of the vehicles, it is quite clear to see. So it's quite aggressive lateral movement, which is seen on from the vehicles on their suspension. This type of lateral movement will inevitably result in high lateral wheel-to-rail forces, which can be simulated and outputted. So to investigate this, in that simulation, transducers were attached to the wheel sets of the digital twin, and these can be used to quantify the lateral wheel loads and therefore the likelihood of a derailment under these extreme conditions. So the graph that we're showing here, it shows high lateral load on the left wheel of the leading wheel set on the impacting vehicle, where the force reaches nearly 300 kilonewtons. We can also see from the many output graphs produced by digital trains the sequence of events that happens during this offset collision. So on the right hand side, we see the force versus time of each interface. Each interface is cascaded against time, so we can see how they interact with each other. Other cascaded graphs will show deceleration versus time, or velocity versus time for each vehicle. And then the left-hand graph, we're showing the force versus stroke of each interface overlaid, with the green one being the impacting interface, i.e. the front of the train. And again, what this is showing us, so this shows us that the coupler is first fully stroked. Then we get the step up in force, which is the inside anti-climber activating, following by the outer one, which is happening afterwards, which is the second step. So again, all the outputs can tell us everything that's happening during an impact. And finally, just like to show an example of a buffer stop impact. So this particular test is of a mega mass freight train in India's new dedicated freight corridor. These trains consists of 88 wagons and a total train mass of 6,500 tons. This actual test was performed at 10 kilometers per hour, so 10 kilometer per hour collision into a buffer stop. And prior to the test, digital trains was used to identify how much sliding space would be required for the buffer stop to arrest this train, and then to correctly configure the sliding friction elements to ensure the train was stopped. And here we see also then the 3D visualization of the impact and the force exhibited on the track whilst the train is being arrested, which is the graph which is being plotted, versus the actual test itself. So before we move into the Q&A session, I'll just briefly summarize what we've covered today. So Digital Trains is a powerful web-based simulation platform that brings together three essential modules: gauging, train running, and impact, each designed to meet critical needs across the railway industry. With gauging, we deliver a fast, accurate way to manage clearance assessment and avoid costly design clashes, essential for any infrastructure or rolling stock project. With train running, users can build high-fidelity digital twins to simulate performance, comfort, and energy use across real-world rail networks. And finally, with impact, we provide a trusted tool for crashworthiness and compliance with safety standards like EN 15227, simulations which are already widely adopted by leading manufacturers and operators. And as we've shown, the software is designed to support every level of the rail supply chain, from design and safety to operations and maintenance. If you'd like to explore any of these in more detail, or if you'd like to arrange a demo, you can reach out directly to Dr. Terry Williams, whose contact details are shown here. Now, myself and my colleagues would be happy to take any questions. So I'd just like to say thank you very much for listening. And yeah, if you have any questions.